Hi, I'm Shenghao, here to give an introduction to our final year project, running CNN efficiently on a FPGA. This project was supervised by Dr. Wei-Chen Liu. This presentation will consist of three main components: the motivations behind this project, the methodology used, as well as the results and conclusions obtained. Starting off with the project's motivations. Edge devices nowadays can take advantage of deep learning models to provide enhanced functionality in areas such as natural language processing and computer vision via the aid of deep learning accelerators. In these accelerator-using devices, sensor data is fed directly to the accelerator, allowing the application's processor to be relieved from the heavy arithmetic required for model processing. To implement these accelerators, FPGAs are commonly used because of their flexibility. Their reconfigurable nature allows for multiple accelerators to be multiplexed on a single FPGA, resulting in a more compact final product. A key issue nowadays is that the computational requirements of models are outpacing improvements in hardware accelerator performance. As such, model compression through software preprocessing is required in order to ensure that future models can still be accelerated via existing hardware. Even though the field of model compression spans many different areas, this project focused on parameter pruning, where redundant model parameters are removed due to its wide body of existing literature. The most straightforward way to perform parameter pruning is via unstructured magnitude pruning, where the lowest magnitude weights are simply removed from a parameter matrix. However, this form of pruning results in models that cannot be accelerated efficiently in FPGAs because of a lack of structure in the resulting matrices. To that end, a significant amount of research has been performed to design parameter pruning variants for efficient hardware acceleration. One of the most influential approaches for FPGAs is magnitude pruning using the bank balance sparsity pruning pattern, where a weight matrix is first split into banks of equal size, followed by removal of the lowest magnitude parameters within each bank to form a sparse matrix. However, the pruning pattern only forms one half of a pruning pipeline. The pruning strategy, defining how the pattern is realized, must also be considered. In Tao et al.'s original paper, only the fine-tuning strategy was evaluated, but not the learning rate rewinding nor gradual pruning strategies. To that end, our project focused on comparing pruning pipelines created from all combinations of the two patterns and three strategies to determine the differences in performance between bank balance sparsity and unstructured sparsity, as well as the best pruning strategy to use with bank balance sparsity in different scenarios. After performing our experiments, we discovered that bank balance sparsity provides acceptable accuracy up to moderate sparsity levels of 60 to 70% relative to the dense baseline, while unstructured sparsity provides significantly better accuracy than bank balance sparsity for high sparsity levels beyond 80%. As such, it is recommended that bank balance sparsity be used for models with moderate sparsity levels to capitalize on it, allowing for efficient accelerator designs, while unstructured sparsity be used in situations where high sparsity is required due to storage constraints. Moving on to inter-strategy comparisons, in use cases requiring the highest accuracy, fine-tuning is the best choice, with gradual pruning a close second and learning rate rewinding providing the worst accuracy. And in scenarios where it is preferable that models be developed quickly, gradual pruning is the best choice because training and pruning takes place concurrently without a need to retrain the model during the pruning process. Lastly, when targeting for the greatest ease of use, learning rate rewinding is the optimal choice because it introduces no additional hyperparameters. To end off, given the changing performance characteristics of a pruning pattern when paired with different pruning strategies, we recommend that patterns in development be characterized on a larger variety of pruning strategies in order to allow for a more robust evaluation of its performance.